So we say OK, and our circle is output. Next, we have to do our alignment feature. So in this case, we're actually going to create an origin, and the origin will be set to x0 and y0 at the center of this circle. Again, what we're simulating here is we've already leveled off our part, so if we look from the front view, our part is not rotated like this or like that. If we look from the right view, our part is not rotated like this or like that. However, at this point, our part can still move back and forth in the x and in the y. So when we say create origin, we're saying that this part is no longer allowed to move along x, it's not longer allowed to move along y. But we are not stopping this from rotating about that c-axis just yet. So our 2 in this 3-2-1 alignment is going to stop x position and y position. Those are two linear axes. We say OK. And now we can also output a tolerance right here. We can say tolerance last element, and we can output the diameter of this feature, and that diameter is going to be plus or minus 5 thousandths. This is a 3-place decimal, so plus or minus 5. And when you do that, just make sure you type in the minus 5 thousandths here. If you forget the minus, you'll get an error. All right, we are not outputting x or y position because, by definition, this is the 0 point of your program. You can't check the position of a datum. So our next move, let's go finish up our alignment. To finish up our alignment, we are going to touch another circle over here on the right side. So let's say we call this the right hole, and we might as well do an output text for this. So we'll go output, output text, and we'll name this right hole, and that will be used for, let's see, balloon number, I should just balloon these, 1, 2, balloon number 3, and it will also be used for balloon number 4. So right hole, x position, and diameter, so we'll see dia, comma x, and that will be b3, comma 4. We say OK, and then we switch back over to Cat 1000, and we'll touch a circle inside here. We'll name this one right hole, or actually I suppose we should call this datum C, that's what it is on the print, and we'll say OK. Now this is very interesting. We have a circle here and we have circle here, but we have nothing to connect the two of them. If we look over at Learn Mode, we see our two circles. Looking from the top view in Learn Mode, we can see there's really no relationship between the two of them. Well, we actually can't do anything alignment-wise with just this circle. We have to create a line that connects the center circle to the right circle. And we'll call this align axis. And we'll call this a connection element. And all of our options go away except for centroid. We'll say OK. And we'll grab only circular features. We'll grab datum B and C, and we will project those up onto the XY plane. So that way if there is a slight tilt where the Z positions were a little bit off, the CMM will ignore that tilt. And we'll say OK. And now let's turn on our graphics here. Looks like our options have not been turned on for some of these elements. And now we can see our connected line right here in blue. So our connected line will be used to constrain our axis. We will say align axis parallel to axis, and we are aligning this axis parallel to the x-axis. Now it is tempting to use this origin on axis command, and I guess in this context that really won't make a difference. But really best practice is to leave the origin set exactly where it was in the previous step of the alignment. Again, it's a 3-2-1 alignment. This did X, Y, and, or I'm sorry, this did A, B, and Z. This does X and Y position. The only thing this will do, this alignment feature that's coming up, will do the C-axis rotation. If we turn this on, that would over-define our Y position. So say OK and cancel. And now we can turn some of these settings back off here. We don't need to see those anymore. And there you can see the line that we created connecting the center of the two circles. All right, looks like our alignment really stayed in the same spot, which is good. We didn't expect to see any movement there. I suppose we should output the diameter and the x position of our last element. Now, unfortunately, that's not actually our last element. The last element is the line, so we'll have to use just regular old tolerance element. We'll have to tell it we're actually going back in time and we want to tolerance that circle, datum C. In this case, we are going to do diameter. It's still 375 plus or minus 5. However, we also want to do balloon number 3, which is going to be our 1-inch dimension. Now for this, we can simply output our x position. So we'll turn on our x coordinate. That should be 1 inch. That's a 3-place decimal. So that is plus or minus 5 thousandths. You say OK. And it looks like the only other thing we have remaining is we have to touch this circle. We have to create a line so that we can output the angle in between the line that connects these two circles and the line that connects these two circles. We also have to output the diameter of this hole, so it looks like we need to touch a circle and then connect it into a line. So we'll get right into that here. Let's switch back into GeoPack again. We will just put a label on this. We'll say output text. And just so we can follow this in the future, we'll call this left hole. And we are going to output our diameter and our length and angle here. And those balloons will be balloon number 1, 2, and 4. So we're going to output balloons 1, 2, and 4. 1, 2, 4, respectively. Oh, I'm sorry, I did that in the wrong order. It's 4, 2, 1. We want these to be respective. We want balloon 4 to match the first thing that we're outputting, balloon 2 to match the second thing we're outputting, etc. Okay, so let's switch back over to Cat 1000. We will touch a circle inside of there. We'll name this one left hole. 4 points is fine for this. It's a low precision measurement. Clearance plane will get us over there safely, and we say OK. Circle comes into the program over here. Now in Learn mode, we have to create a line. Again, this is going to be a connection element, and we'll name this angled line. We'll say OK. And we are going to create this out of datum B, that's the center hole, and the left hole. We'll project this onto the XY plane. We'll use measured points. And you can see that they turned red here. This is datum B, this is the left hole, and we'll say OK. Now we can see this line that comes through the center of the two holes and this line that comes through the center of the other two holes. So next we can tolerance element, and we will tolerance the diameter of the last hole that we touched, which is the left hole. Now here we can only output our diameter, and then we'll output our angle, and this would be angle X, and we will also output our distance. Now notice this is distance and not X coordinate or Y coordinate. If you did X coordinate, that would be the distance horizontally from here over to the center of this hole. Now I have the mouse over here because the center of this hole, if only measured in X, only gives you this distance. We could also use the Y coordinate, which would only give you the distance from datum B up to the Y coordinate of the hole. Neither of those are what we want. We want the two-dimensional distance as the bird flies from the center of one hole to the center of the other hole. So these numbers should be directly on the print. It looks like our 2D distance here should be 1 inch. It looks like our angle here should be 45 degrees off the edge. I think to get that to come into the dimension report, it may actually have to be 135 degrees. 180 minus this value. So this dimension should be 1 inch, and that is plus or minus 5 thousandths. And this angle X should be, I'm guessing, 135 degrees, plus or minus. Let's look at our title block here. Angles are plus or minus 1 degree on this print. So plus or minus 1 degree. We will say OK. And then we'll take a look at our list of results here. And if your list of results are way off, well, that usually means that either your CAD model's off or your programming is off. Now in this case, I can see I was correct about the 135-degree angle. Really mathematically equates to the exact same thing as 45 degrees. We're just adding in that extra 90 degrees. Down here, distance from origin of our angled line, I see that we are supposed to be 1 inch plus or minus 5. However, we're deviating by minus 955 thousandths. So that tells me that I've set that up incorrectly. So let's get rid of that tolerance and say yes. And let's add that back in. So it turns out I was actually missing one field here. You actually have to create a distance for this length. It does not allow you to do that as just a line. So we have to actively come in here and create a distance. So create a distance here, and we'll call this distance center to center. We'll make a distance between a circle that is datum B. That's this circle right here. Notice it shows you element number 1. And element number 2 is going to be the left hole. We are going to do a distance without compensation. That means the distance will come from the center of the circle to the center of the other circle. We could do tangency to tangency or far tangency to far tangency. That's what these options are. We'll project this onto an XY plane. Of course, when you do this, you have to choose a projection plane. So say OK, and notice that now the default distance is coming in as 1 inch. Much better. Notice also I'm putting these in an order so that it matches the output text here. The left hole is going to be diameter first. That's this tolerance. Then length. That's this tolerance. And lastly, we'll do the angle. Notice also that that nice tolerance last element trick does not always work when you do this, because now the last element was this center to center distance. All right? So we can always come over here and just tolerance the element instead of tolerancing last element. In this case, if we're trying to do the angle, we'll tolerance the line, and the line will be the angled line, and say OK. And our 135 degrees plus or minus 1 degree is still here. Of course, this distance didn't turn out correctly, so we'll uncheck that and say OK. So one last double check over the print. We do have balloon number 1, that's 45 degrees. We have balloon 2, that is our length from center to center. We do have balloon 3, that's our center to center distance from datum B to datum C. And then we have our diameter times 3 features. So it looks like we are ready to end our program here. We'll go program, subprogram, and end block. Say OK. And it'll take a second to think here, and it will generate the dimension report. Aha! So there is another error here. I made multiple mistakes. Let's see. Do we have everything? We have datum B diameter is 375 plus or minus 5. That looks good. Let's do a left screen, right screen trick here, so we can see our print side by side. All right, so we have 1 times 375 is good over here. We have 2 times 375. We have datum C is 375 plus or minus 5. That looks good over here. And then lastly, we have our third diameter, 375 plus or minus 5. Looks good. That's this diameter here. For our position X, that is the distance in between this datum B and datum C. We have 1 inch plus or minus 5 is good. For our distance XY, that's giving us red here. And the reason it's giving us red is we did actually measure that at 1 inch, but notice that the high limit tolerance is plus 5. The low limit tolerance is also plus 5. Okay, so I simply forgot to put a minus sign in there, but man oh man, details make a big difference when it comes to coordinate measuring machines. We're now done with our CAD model, so we can close that out. We'll come back into the editor here. And the problem actually lies right here. The problem is this minus sign that is missing. We'll add that in there and say OK. We'll save it and then come back and run that in repeat mode. And at the end of all that, our dimension report comes out correctly. All right, so now we can see that this 1 inch plus or minus 5 is actually plus 5 and minus 5, and we are good to go. Of course, we're measuring off a CAD model that is theoretically perfect, so it shows us we're right in the center of the tolerance everywhere. Your next move would be to do a plate check to verify each one of these using a precision hand gauge.